Okay, this is lecture 6. So we're going to talk today about the unconditional jump. We previously mentioned that there are three types of instructions. The first type is data movement instructions. Instructions with which we can move the data from a place to another place, from a register to a memory location, or bringing data in or sending data out through the I/O ports. So this is the first kind. The second category of instructions is the arithmetic and logical instructions, instructions with which we do arithmetic and logical operations. The third and last type of instructions are those instructions with which we can control the flow of the program. One of these instructions is the jump, and the jump is of two types: unconditional jump and conditional jump. Unconditional jump, you do the jump without checking any condition. No check, no conditions to be checked before you do the jump. Okay? Unlike the conditional jump where you have to test one of your, for example, one of your flag bits, whether they are set or cleared before you do the jump. So now we're talking about the unconditional jump. Regarding the unconditional jump, we can also talk about two kinds of unconditional jump. The first is called intra-segment unconditional jump, which means you do the jump within the currently active code memory segment. And this intra-segment could be short or near. Okay, so this is the first type, the intra-segment. The second type is the inter-segment. Inter-segment meaning you jump between code memory segments, not within a code memory segment. So you will have to leave the currently active memory segment to another memory segment, code memory segment. You need to activate it. And we call this inter-segment, or the jump between code memory segments, a far jump. So we have short, near regarding the intra-segment jump, and we have far regarding the inter-segment jump. Regarding the intra-segment jump, again, it's intra-segment. You do the jump within the current code memory segment. So the addresses are limited to the currently active code memory segment. You don't go outside. And you do this by modifying the value inside your instruction pointer. So change the value inside your instruction pointer. You do not change the value inside your code memory segment. Only IP is going to be changed. Again, as we said, it could be of a short type or a near type. So now what is the difference between a short jump and a near jump? We'll talk about the short and near shortly, but let's introduce as well the inter-segment jump, which is used and done by modifying both the values inside your code memory segment and the value inside your instruction pointer. So you have to change your code, the value inside your code memory segment, because you intend to leave this currently active code memory segment to another code memory segment, and you do this by changing the value of your CS, which holds the starting address of the new current code memory segment. Okay. The machine codes for the unconditional jump. All right. This is EB for the short, E9 for the near, EA for the enter segment. Regarding the short, you add only 8 bits, a displacement composed of 8 bits, while near you add 16 bits. You change the low byte of your IP and the high byte of your IP, while the enter segment jump, you change both low byte and high byte of your IB and low byte and high byte of your CS. So both IP and CS are going to change when you do enter segment jump. Okay. Short jump, this is a displacement. And it is short because it is composed of 8 bits. If you have 8 bits, you can do jump forwardly 127 bytes or backwardly 128 bytes. So you are somewhere within your code. You can go upward up to 127 bytes or downward up to 128 bytes. And what determines whether you go up or down is the direction bit in your flag. So if you intend to go up, you reset your direction bit. If you intend to go down, you set your direction bit. Okay. The near jump, you use 16 bits. This is why you can go forwardly up to 32K bytes and backwardly up to 32K bytes as well. Okay, we're still in the unconditional jump. So this is an example now. Jump 04. What kind of jump? This unconditional jump. It's unconditional because we did not check any of our flag bits to be set or reset. It is unconditional jump, and the operand is of 8 bits. So we have 8-bit operand, which means this is a short jump. Okay, so this is before execution. This is the value inside your CS, and this is the value inside your IP. What this short jump does is this. It doesn't leave the currently active code memory segment, so CS will return its value, while IP is going to be modified, and you go up 4 bytes. Okay, so this is after execution. This is your new IP. You add 4 to your IP, it becomes 6. This is where you're going to resume your execution. All right, here, this is a 16-bit operand, which means what? This is a near jump. What a near jump does is this. Again, it doesn't change the value inside your CS, and it will replace the value inside IB, the value inside your IP, by a new value now. So after execution, this is your new IP, and CS will remain intact. Good. Another example. All right, this is jump, and we provide 32, not 16, 32-bit operand. Why 32-bit? Because this is a far jump. In a far jump, you need a new value to be placed in your code segment register, CS, and another new value to be placed in your instruction pointer. So this is your new CS. So we're going to leave the currently active code memory segment and go somewhere else. And this somewhere else has a starting logical address of A300. And within this new currently active, within this new code memory segment, you will start executing a program whose starting address is 0127. So before execution, both CS and IP, these are the values before execution. Definitely you are going to change both CS and IP after execution. This is your new CS A300, and this is your new IP 127. So now you are in a new code memory segment starting at this address within this new code memory segment. Okay, another example. Okay, how could we identify this jump? Is it short? Is it near? Is it far? Well, check your operand. If your operand is 8 bits, it's a short. If it is 16 bits, it's a near. If it's a 32 bits, it's a far. Here, the address at which we would like to jump is placed in BX. Good. BX refers to some location or locations in memory. Would you consider the logical address inside BX to point to a byte and get 8 bits, or 2 bytes and get 16 bits, or 4 bytes and get 32 bits? Well, the default address locations you get is 2 bytes, 16 bits. Okay, so when jump BX is not preceded by a byte or a double word pointer, it is used to point to 16 bits in your memory. So you go to memory and get 16 bits, which makes the default jump by this notation is a near jump. Okay, good. So you go now to your memory. This is your CS. It's not going to change because we said this is a near jump. This BX, which takes you to the memory, the data memory segments, and you go there and get 16 bits. The one which is pointed to by BX, and you automatically increment it one location up, and you get 8 bits from here and 8 bits from here, and these values are going to be replacing the value inside your IP. Okay, so this is the value, the current value inside your IP. After execution, before you do the execution, you need to go to the data memory segments. This is the value pointed to by BX. You go one place up, you collect 8 bits, low in low and high in high, to get the new value to be placed in your IP. Okay, good. After the execution, this is your new value inside your IP, and CS will be kept intact. You don't change it because this is a near jump. You jump within the currently active code memory segment. All right. The physical address you will start at is obtained by CS times 10. You add to this IP, and this is the 20 bits physical address of the starting instruction in your new code to be executed. Good. Another example, jump. Well, bx now is used, but you go to the memory and collect 32 bits because you're using here a double word pointer. So when you go to memory, the place pointed to by bx is the lowest addressed memory location. You go one place up, another one place up, a third one place up to collect 32 bits. And of course, when your operand of the jump is 32 bits, this is a far jump, which means you would have to change both your CS, your CS, and IP. Good. Well, this is now the lower address 2 bytes, 0, 2, high and high, 0, 0. This is for your IP. And the next lowest or the highest two addressed bytes are 0A, high and high, 10, low and low. This is your new value of CS. After execution, this is your new value of CS, and this is your new value of IP. Good. Now we go to the second type of jump, which is the conditional jump. Conditional jump means what? There should be some condition to be checked before you do the jump. If the condition is satisfied, you jump. If it's not satisfied, you go to the next sequential instruction and start executing from there. Good. And this is the mnemonic code. Jump after checking some conditions. Okay. And the operand used with the jump is always of a short type. It's always of a short type. So regarding the conditional jump, you're only allowed to go upward up to 127 bytes or backwardly up to 128 bytes. You don't go further, okay? You don't go beyond this limit. Good. So they are all of short jumps. So operands are always 8 bits, 8-bit operands. Okay. So you're allowed only 127 backwardly or 127 bytes forwardly. And there is a list of the conditional jump. For example, here JC, which means what? Jump if the carry flag bit is set. So first you go and check, is the carry flag bit set? Okay, if it's set, you do the jump. For example, here, jump if equal, which is equivalent to jump if 0. You have two numbers. Are these two numbers equal? Or if the difference between them is 0, you go and check your 0 flag bit. If your 0 flag bit is set, this means the two numbers are equal or the difference is 0, you do the jump. And likewise, each and every other instruction. Okay, for example, this one, jump if not overflow. So if your overflow bit is 0, which is meaning you don't have any overflow, you do the jump. So usually when you check the condition, you use your flag bits. Okay, except for this one, which is CX, because CX is the counter register, so you can do the jump after executing a portion of your code several times, 3-4 times. The 3-4 times, this number 3 or 4 is usually stored in CX. So every time you have to check your CX. If it is 0, you jump. If it's not, you don't jump. All right. Example, trace the following program. Okay, compare AX, BX. What this instruction does, it calculates the difference AX minus BX. So it's a sort of subtraction, but it, it differs from subtraction in this way. When it does calculate the difference, it goes and modifies your flag bits, which means if this difference, for example, is 0, it goes and set the 0 flag bit. So the difference itself, the result of this subtraction operation, is not saved or stored anywhere. It is only used to modify your flag bits. So here we do this and modify the flag bits. Okay. Jump if below to somewhere which is named def2, which means if this subtraction you are AX is lower than BX, if your AX is below BX, which means you would need definitely a borrow and your ALU sets the carry flag bit. So if the carry flag bit is 1, this means AX is lower than BX and the condition of this jump will be satisfied and you would have to go to def2. Okay, so now the condition is satisfied. You go to def2. What this def2 does, it takes the value of the bigger number bx, place it in dx. Then it subtract now dx minus ax, which means what? This is definitely becomes a positive now. And if you go to the carry flag bit, you would find it 0. All right, and you're done. Otherwise, if your carry flag bit here was not set, which means your AX is higher than BX, okay, so now you place the value BX into DX, okay, and then your BX is not below, your AX is not below, AX is higher than BX. So you take the difference, AX minus BX, and place it in DX. So when BX is lower, you take the difference, place it in AX. When BX is higher, you take the difference, place it in DX. As if this code it checks the difference between AX and BX. If AX is higher or BX is higher, in both cases, the absolute difference now is placed in DX. So the value inside DX is always positive. So you check. If AX greater, you make AX minus BX, place them in DX. If AX lower, you take the lower beside the negative sign, you calculate BX minus AX and place it in DX. Good. Let's trace another program. Now, this instruction is saying what? What this instruction is trying to do? Well, it takes the effective address or the offset of an array named table and place it into DI. So now DI points to the first entry of an array named table. How many elements does this array contain? We don't know yet. What are we trying to do? We'll see when we scan the rest of the program or trace the rest of the program. But at least now we know that this instruction makes di to point to the first entry of an array named table. Well, we're placing 100 in Cx. It seems that we're going to do something 100 times because Cx is our counter now. Alright, good. Load your AL with 0A. We're placing 0A in AL. Clear the direction flag bit, which means what? Starting from an entry, you are going to go upward to check the second, third, and fourth, meaning you're going to increment our index DI, not to decrement, because we're clearing the direction flag bit. If the direction flag bit is cleared, you place a 0 in there. This indicates you're going to move forwardly within your array or block of data. Good. Here, what we're trying to do is this. We are going to repeat of not equal. Repeating what? We're scanning these 100 elements. We check every element we read against 0A. Alright? So this is scan string byte by byte. This instructions is repeated if every byte to be scanned, to be checked against 0A is not equal to 0A. So it seems that we have a table or an array of 100 elements, and we are trying to check every element starting from the very beginning against 0A. Okay, and we are going to repeat this. If we don't find 0A within these 100 elements, we are going to repeat it. So if the first element is not equal to 0A, we go to the second element. If the second element is not equal to 0A, we go to the third element, and we do this scanning till what? Till Cx is 0. If we scanned the total 100 elements in this table and we never found 0A inside, we have to jump and say we did not find this. Jump if Cx, this is what this instruction means. It tells your program to jump if Cx is a 0 and jump to a label saying not found. We did not find a 0A value within these 100 elements. Good. So this program scans a table of 100 bytes for a value of 0A. Okay, another important instruction with which we control our programs is the loop instructions. Sometimes when you do programming, you may need to go over a portion of your code several times. To be able to do this, there is an instruction designed for you which is loop. So the loop instruction enables programmers to go over a piece of code several times. And you can do this conditionally or unconditionally. So we have two different types. Unconditional looping, so you loop without checking any condition to go inside the loop. All right, you loop several times, you execute a portion several times. These number of times you need to go over this piece of code, we call each time an iteration. How many iterations you need to do? This number of iterations should be placed in your Cx. And you do the looping without any condition to be checked. The second type is the conditional looping. So you check a condition. If this condition is met, you go inside your loop and do the looping. Go over this piece of code as many times as you wish, as long as the condition is satisfied. Okay, so the unconditional looping, you don't check any condition, as a matter of fact, can be looked at as a conditional jump and decrement the value inside your Cx. It's unconditional. You don't check a condition before you enter the loop, but as long as you are within the loop, after each iteration, you decrement your Cx by 1 till the value inside your Cx becomes a 0, you go outside the loop. So it always decrements the value inside your Cx register. If your Cx is not a 0, you do looping. If it's a 0, you go outside the loop. All right. The conditional loop instructions are these instructions. You loop if equal. You have two numbers. If these two numbers are equal, you check. You go to the and do one more iteration. You loop. And loop if equal is exactly equivalent to loop if 0. So if the difference is 0, loop, which means they are equal. Here you loop if these two numbers are not equal or the flag bit is not set, which means the difference is not a 0. Okay. The loop instructions, the conditional loop, as a matter of fact, it checks for two conditions. The content of Cx and the 0 flag. If we're talking about loop if equal or loop if 0, after each iteration, you check your 0 flag. If the 0 flag is set, which means the two numbers are equal or 0, you do looping. If it's not set, you check your Cx. If it's not yet 0, you do looping. So you loop as long as the two numbers are equal or the number of iteration you required by your code has been reached. And this is checked within the value inside your Cx. You check this by the value inside your Cx. If it's a 0, you terminate the loop. If the numbers are not equal, which means the 0 flag is not set, is a 0, you terminate your loop. So if Cx is not 0 and the if condition is satisfied, you do the loop. If Cx is 0 or the condition is not satisfied, the f is not 1, you terminate your loop and go to the next sequential instruction. All right, and this table shows the mnemonic code of the loop instructions. And remember, they are all of short type. So you don't go away from where you are by more than 128 backwardly and 127 bytes forwardly. And each time you do an iteration, you decrement the value inside your Cx. Okay, let's take an example. Move 5 into Cx. It seems that we are going to do a maximum of 5 iterations. Place 0 in dx. Wait for a while. Increment dx. The initial value is 0, and we are going to increment dx by 1, of course. And we need to loop to this place. All right. Well, we don't have a condition to check. So we are going to go to again 5 number of times till the value inside your Cx is 0, which means you are going to increment dx. First iteration, dx becomes 1, second, third, fourth, and last iteration. So you go outside the loop whenever the value inside your dx becomes a 5. Okay, so your loop is terminated when dx becomes a 5, at which your Cx becomes a 0. Example 2. All right. Now we're placing 5 inside DL. Good. And we're moving this value inside your AX. And we're moving this value inside your DS, which means we are going to start at a certain code memory segment whose logical starting address is this, the value placed in your DS. Good. Then we have a source index. Looks like we're going to scan some portion of your memory starting at this 200 hexadecimally. All right, we're going to do this 15 times, a maximum of 15 iteration. We are going to increment SI to go to another value inside your memory. Okay, starting at 200. So we are going to start here at a logical address of 200. Okay, this location is pointed to by your SI. Good. Now you compare the value at this SI by the value inside your DL, which is 5. Okay, well, if they are not equal, if the value you picked is not equal to 5, you do and loop again. So this tells you that we started at some location inside your memory and we are looking at 15 different locations starting at this one, and we are checking whether the values inside these is equal to the value inside DL or not. So if you pick the value which is not 5, okay, you loop again and go to the higher addressed value. If it's not a 5, you go to the higher one. You do this till you either finish 15 locations or you find one of these locations equal to 5. Okay, good. Well, this is a comparison loop. You do this until either Cx becomes a 0 and you don't have 5 within these 15 bytes, or Zf becomes a 1, which means you found the value 5 within these 15 memory locations. And we'll explain this further by this slide. Okay, we have a block of data pointed to by SI, and we are comparing each value at which or to which SI points to with the value inside your DL. So for example, if this is the starting address of your data memory segment and the 15 memory location contains these values, and we are trying to scan and check these 15 values for a value of 5, and if you look closely, the fifth value within these 15 memory location is equal to 5. So you do your first iteration, the first loop, first iteration. First iteration will pick 4, compare it to 5. ZF is 0, they are not equal, and you decrement your CX by 1. Then you'd have to do one more iteration. Second loop, you pick 6. 6 is not equal to 5, your 0 flag bit is not set. You decrement your DX and go to a new value, which is 3. 3 is not equal to 5. You go to a new value and decrement CX. You pick 9. When you pick 9, 9 is not equal to 5. Your 0 flag bit is not set. You go to a new value. You decrement your DX. Here, fifth loop, the value is 5. 5 is equal to 5. So your 0 flag bit is set. you go outside the loop, you terminate the loop. You don't have to do any more iterations because you found the ID you were looking for. So this should be or could be a list of some IDs, and you check whether the coming ID of 5 is within your list or not to let him in. Okay, so now you terminate your loop. Okay, another very important technique used in writing codes is known by subroutines. Subroutines, what are these subroutines for? Subroutines, sometimes when you write programs, you may require to do calculations by executing a portion of your codes. And you need to do this calculations several times. For example, you calculate cosine x many times in your code. You need to calculate cosine x where x varies. Instead of writing a code at each required cosine x to calculate cosine x, you may write it once and place it somewhere in your memory, call it a subroutine, and whenever you need to calculate cosine x, you go to this portion, you go to this subroutine, calculate it, and bring into your program the value of cosine x. So you need to write it once and execute it several times. So this is the beauty of your subroutine. If a portion of a code needs to be run several times, instead of writing it several times and eating up your memory, you just write it once, and whenever you need it, you call this subroutine, execute it, and bring in the value to your code. So subroutine saves memory because you write it once. But the disadvantage of this, it takes some time. It delays your code, the execution of your code, because time will be consumed in calling this subroutine and returning from this subroutine. All right, so it's a group of instructions needs to be executed to perform some task. Instead of writing it many times, you need to store it only once and call it as many times as you wish. This definitely saves memory, but at the expense of some time that should be consumed in calling and returning from this subroutine. And this is the end of lecture 6. We see you in lecture 7. Okay.